It's my pleasure to introduce Tristan Bice. I really want to thank Tristan for coming all the way from the Czech Republic for this. He wins the prize for traveling first to the conference. So, yeah, thank you. So, without further ado, here's his talk.
Yeah, thank you for the intro. And yeah, well, I'd like to thank you, the organisers, for putting this on. It's really nice to be able to be at my first real conference in such a long time. So yeah, really enjoyed it. It's been lovely to meet all of you guys. So yeah, today I wanted to talk to you a bit about some dualities I've been playing with between certain rings and semigroups and certain kinds of groupoid bundles. Right? So, this is the long title. There's, I think, the shorter title in the abstract, etc. But here we go. So first, maybe just to give you a bit of an outline of the history, I thought I would tell you about a few classic dualities that take this kind of a form. So there are dualities between certain commutative rings or algebras on the one hand, and on the other hand between certain topological spaces, or maybe sometimes bundles of rings over those spaces. So for example, you're probably familiar with the classic Gelfand duality between commutative C-star algebras on the one hand and locally compact Hausdorff spaces on the other. So, I mean, you probably know this, right? But so given such a space, look at the continuous complex valued functions, vanishing infinity. That definitely gives you a C-star algebra. And Gelfand's key realization was that in fact all commutative C-star algebras have to be of that form, up to isomorphism. And also it works, it's functorial as well, right? If you have a continuous proper map between the spaces, even a partial map, this is going to give you a C-star algebra homomorphism in the opposite direction. And all C-star algebra homomorphisms between those commutative C-star algebras have to be of that form. A more sort of algebraic kind of analog of this is due to Kleiman. So he showed that if you have idempotent generated torsion-free commutative algebras, that these are in fact dual to zero-dimensional compact Hausdorff spaces, generally called Stone spaces. So again, it works pretty much the same way. So given such a space, you look at all the locally constant scalar valued functions that will give you one of these idempotent generated rings or algebras. And Kleiman showed that in fact all such algebras actually have to be of that form. And again, it's functorial as well. Maps between the spaces correspond to homomorphisms between the algebras. A little bit before Kleiman, there was actually some even kind of more general work done by Pierce and Dauns-Hofmann. And they were looking at biregular rings. So biregular, I think, just means that what every principal ideal is generated by an idempotent. So it's another kind of condition saying you have a lot of idempotents. And they showed that these are dual to bundles of simple rings over stone spaces. So again, given such a bundle, you look at its continuous sections, that gives you a biregular ring. Conversely, all biregular rings have to be of this form. And there is again this functoriality, although it's a little bit more sophisticated because the morphisms between the bundles have to be some kind of interesting combination of a map between the base spaces as well as a map between the fibers. But we'll talk a bit more about that later. Okay, but here's the sort of the key question that you would naturally want to ask is, can we do non-commutative versions of all these kinds of dualities? So I guess the third one does officially apply to even non-commutative rings. The only problem is this third one can be quite trivial, in the sense that if you start with a simple ring to begin with, the corresponding bundle will just be that ring over a single point, which doesn't really tell you much. So even in the third case, this is really not as non-commutative as you would really like. So there are some recent non-commutative extensions of the classic Gelfand duality, or at least things that could be viewed in this way, due to Kumjan and Renaud. And so they show that now not just single C-star algebras, but certain Cartan pairs of C-star algebras are dual to twisted, effective, locally compact Hausdorff tile groupoids. So a Cartan pair consists of one potentially non-commutative C-star algebra with a sufficiently nice Cartan commutative subalgebra. Right? And they showed that, well, if you've got one of these, it's easy to produce a Cartan pair. Conversely, every Cartan pair has to be of this form. However, there is sort of, even here, there is something missing in a sense that they weren't really so interested in morphisms. I mean, I guess they looked at isomorphisms, but they weren't looking at more general, groupoid morphisms or functors versus Cartan pair homomorphisms or anything like that. So even here, there's still sort of some work to be done. I've done a little bit of stuff on this recently, although I won't talk about this today. If you want an analogue of Keimel's work, well then there's this very recent paper by quite a number of authors. So so they showed that they were sort of inspired by the Caesar algebra theory, and so they looked at what they called quasi-Cartan pairs of algebras. So again, it's a one large, potentially non-commutative algebra with a sufficiently nice commutative subalgebra. And they showed that these are dual to twisted effective ample groupoids. And so again, given one of these, you look at the locally constant, compactly supported functions. These naturally give you a quasi-Cartan pair, and all of them have to be obvious. And again, there's this, an issue of could you make this really, truly functorial in a nice way? But then there's the natural question, well, what about number 3? Is there also a natural non-commutative version of that, something more general? So it's not too hard to define what a bundle of rings, or really more a ringoid over an ample groupoid would be. You could look at the sections. That will also give you a kind of ring. But the question is, what kind of rings does this get you? I mean, what is there some kind of natural algebraic conditions, kind of like these quasi-Cartan pairs, Cartan pairs, or whatever? Could you similarly get some pair of rings satisfying some simple algebraic conditions, maybe with a bit of extra structure, that you could put in a duality, precise duality with these bundles here? And could you also make that functorial? So that's the big question, and that's why I wanted to show you today how you can do this. But to be completely honest, I'm not actually going to talk much about rings. I'm actually really going to talk to you much more about semigroups. And the reason I can do that is because there is a kind of parallel, series of works on various other kinds of semigroup or lattice, semi-lattice dualities. And these all go back to this classic stone duality between Boolean algebras on the one hand and stone spaces, hence the name. Right? So Boolean algebra is just a special kind of distributive lattice. And I'll talk a bit about this more later, but suffice it to say that even up until the present day, there has been quite a bit of work on generalizing this duality to various more general kinds of lattices and also more general kinds of spaces. But more interestingly, for me at least, there has been some recent work which kind of parallels these ring theoretic dualities. So there was a nice bundle equivalent of this duality, which was worked out recently by Lawson and Kudrat-Sever. So they showed that bundles of stone spaces, one stone space over the other, these could be put in duality with a kind of non-commutative version of a Boolean algebra, a skew Boolean algebra. They also had some other, I guess, even more non-commutative variants. So firstly, this was actually, I guess, just Lawson back in 2010. So we had this non-commutative stone duality, which has received quite a bit of attention. And then later with Kudrat-Sever, as kind of a corollary of some other more general stuff they did, they extended this to a duality with what they called Boolean restriction semigroups. And they generalized from ample groupoids to ample categories. But again, there's the question, what about, could we somehow get some kind of bundled version of this? Again, not too hard to define what an ample category bundle over an ample groupoid would be. Look at the sections, you get this semigroup, but what kinds of semigroups does it get you? Is there a nice algebraic kind of characterization of these kinds of semigroups? Perhaps maybe the semigroup is not enough. Maybe you also need some kind of nice sub-semigroup like you had in the ring theoretic work there. And moreover, could you somehow actually use this to prove the ring theoretic results? Right? Up until now, these two sort of streams of research have been fairly disjoint, but I would claim that this is not really how it should be. I mean, in ring theory, people are usually very concerned with ideals. In semigroup or lattice theory, they're usually very concerned with ultrafilters. But it would be nice if maybe even with rings, you could still use ultrafilters and somehow use this kind of more general work and just with a little bit of extra additive structure get to these nice ring theoretic dualities we could see on the previous page. So this is what I wanted to talk to you about today. So first, I thought it might be good just to quickly review this classic stone duality, which I'm not sure if would be so familiar to everyone here. So to start with, let's just take a stone space. Remember, just zero-dimensional compact Hausdorff. And that tells you, well, you have a lot of Clopen sets, right? These form a basis for the topology. And they have a very natural order structure, just given by inclusion. And you very quickly see that this order structure has some very simple properties, right? So it's bounded, the empty set is the smallest Clopen, the whole space is the largest Clopen. You've got meets or infima, these are just intersections. Likewise, a union of Clopens is again Clopen, these give you the joins. Complements of Clopen are Clopen, these are also lattice theoretic complements. And last but not least is this distributivity condition. So with unions and intersections, this is pretty obvious, right? But with general lattices, this is an extra condition you need to state explicitly. So it's easy to get a Boolean algebra from a stone space. The next question you might ask, if you're going sort of towards the duality direction, is whether this Boolean algebra you get really encodes the space in some way. Does it really have enough data? Could you recover the stone space in some way, just from the Boolean algebra that you've produced? Indeed you can. So what you do is you take a point in your stone space, and this defines a very natural subset of your Boolean algebra. What you do is you look at all the Clopen sets containing that point, and that forms what's generally known as an ultrafilter, maximal proper down-directed subset. And so all these conditions are fairly obvious, right? Like the empty set definitely can't contain the point x. If you've got something which contains x, well then surely that larger thing also contains x. Intersections of things containing x contain x. That's down-directedness, and the fact that given any Clopen, either that or its complement has to contain x. That's what gives you maximality. The more interesting thing to note is that in fact all ultrafilters have to be of this form. It's a fairly simple proof. You just say, give me an ultrafilter. Notice it has the finite intersection property thanks to this downwards directedness, so the intersection is non-empty. Then note that it can't consist of more than one point because you have maximality here. So therefore it has to be a single point. And with just a little bit of extra work, you show that actually it had to be precisely u of x for that point x. So we have a bijection between the points and the ultrafilters in the Boolean algebra. And moreover, you will quickly note that under this bijection, the Clopen set, some Clopen set O, gets mapped to, in fact, the collection of ultrafilters containing that particular Clopen set. So this, you can see that this would sort of define a very natural topology on, a collection of ultrafilters. And with respect to this topology, this map is now not just a bijection; it really is a homeomorphism. So you can indeed completely recover the space just from the Boolean algebra. And that also gives you a clue as to what to do in the sort of final stage if you're setting up this duality. What happens if you start with an abstract Boolean algebra? Well, now you look at its ultrafilters, give it this nice topology where the basis is just all ultrafilters containing some fixed element of your Boolean algebra. You can then, one way to do this, you can then identify your ultrafilters with their characteristic functions, right? And then the topology you've defined there happens to be exactly the subspace topology coming from these characteristic functions. And and it's not too hard to show that this is indeed a closed subspace. And it's pretty easy to see that this is going to be a stone space, right? Was it compact, zero-dimensional Hausdorff, right? Same with products, same with closed subspaces. So you've shown that this is a stone space. So long story short, we've shown that these two operations we have, going from Boolean algebras to the ultrafilter space or spectrum, going from the space to the Clopens, these give you essentially mutually inverse maps, modulo isomorphisms. So it really is a duality. And there's this extra sort of functoriality aspect, but I won't go into that just quite yet. So yeah, hopefully this classic work is clear. Right? What about non-commutative work? So again, I don't want to jump right into the new stuff I've done. I thought it would be better to review Lawson's non-commutative version of the stone duality. So, well, first, I guess, for people here, I don't have to tell you what a groupoid is, but suffice it to say, my groupoids don't have objects. So I view groupoids just as some partial associative product on a single set, which you can consider as the morphisms or the arrows or whatever, I don't like objects, I just like units, right? So, and well, you've got these conditions, right? Idempotents have to be units, and everything has a unique inverse, right? Which then determines the source and the range. The bisections or slices play a particularly important role in this duality here. So a slice, or as everyone probably knows, is just a subset such that the range and source are injected. And you immediately have a nice semigroup structure on these slices, just given by basically taking products wherever you can, right? So the associativity of G passes to the operation you have on these subsets now. And it's not just any old semigroup, it has some nice properties. So you'll notice that your idempotents in the semigroup, these are the subsets of the unit space. But when you multiply these, well, this is just intersections. And that in particular is commutative. So we know idempotents commute. And moreover, if we have a slice where you look at its inverses, again a slice, and these inverses really do behave like a kind of generalized inverse. And these are exactly the defining properties of an inverse semigroup. So we know these slices or bisections form an inverse semigroup. There's also a little bit of extra structure floating around. So again, the key, the natural order structure is coming here from the containment relation. But here it has also a nice little algebraic characterization, given like so. And that is precisely the way you would normally define the canonical order on an inverse semigroup. So this corresponds exactly to containment. And knowing that, you see that these bisections here, they form a meet semilattice, where again, meets are just intersections. Intersections of slices, right? Easy. There's a slight difference now in that we don't have a joint semilattice anymore, simply because a union of two slices may not be a slice, right? You have one arrow in U, one arrow in N, which share a source or a range, right? However, they are almost a joint semilattice, in the sense that if you restrict to orthogonal pairs. So again, there's this algebraic notion of what it means to be orthogonal in an inverse semigroup. If you restrict to orthogonal guys, then these do indeed have joins, just coming from unions. And in fact, orthogonality is precisely saying that these guys are disjoint and that their union is still a bisection. What else? So if you look at the idempotents now, then these, in fact, even when they're not disjoint, these do have joins, again, just coming from unions. They also have relative complements in the set theoretic sense. And so they have these kind of Boolean algebra-like properties, and indeed, and distributivity also holds, right? Just within these idempotents. So again, this is these kind of Boolean-like properties, and these are exactly what Lawson would call a Boolean inverse semigroup. So we know the bisections form a Boolean inverse semigroup, which is great, but it still doesn't quite get us what we want because we haven't introduced any topology. This will not give us all Boolean inverse semigroups at this stage. So next, I have to introduce a topology. So maybe this is not the standard definition of a tile you're used to, but it's one of my favorites. So a groupoid, a topology on a groupoid, I should say, makes it a tile. It's an tile topology, precisely when you have some basis of open bisections which is closed, undertaking inverses and taking pointwise products. Or equivalently, this is saying that all open bisections form both a basis for the topology and some inverse subsemigroup of the collection of arbitrary bisections. Or maybe this is more what you're used to. It's just saying that all the structure maps have to be continuous and open, and hence locally injective, and hence local homeomorphisms. Ample is pretty much the same idea, except we're now looking at compact open bisections. So, and I will, just for the sake of simplicity, only when I say ample, I will automatically assume Hausdorff. So not all people would do this. Some people wouldn't have any Hausdorff conditions. Some people would only assume the unit space is Hausdorff, but I will just assume the whole groupoid is Hausdorff when I say ample. So the Hausdorff topology is ample if it has a basis now of compact open bisections. Again, closed undertaking inverses and products. Or equivalently, you can look at all open bisections, compact open bisections. They have to form an inverse subsemigroup of this guy. Or equivalently, this is saying G is not only a tile, but also zero-dimensional and locally compact. Now you'll notice that when you're dealing with these compact open bisections, that all the relevant operations still leave you with compact open bisections. Right? Intersections, relative complements, unions, as long as you're dealing with orthogonal compact open bisections, right? These will again give you compact open bisections. So these tell you that this forms a Boolean inverse semigroup, or a Boolean inverse subsemigroup, right, of this larger guy here. And the interesting thing is that this is actually going to give you all the Boolean inverse semigroups that you can find. How do you show that? Well, again, you do essentially what we did before, right? Take a Boolean inverse semigroup and look at its ultrafilters with respect to this canonical order. Give it exactly the same topology as we had before, where the basis is all ultrafilters containing some fixed element. Now this also has a very natural groupoid structure, just coming from the product in your semigroup. So, the inverse operation is easy. It's just taking all the generalized inverses in your inverse semigroup, and the product, like I said, if you've got two ultrafilters, you just take all the individual products of U and V. The only issue is this may not be upwards closed, but just take the upwards closure and you'll be fine. As long as 0 is not in here. As long as 0 is not in the products, then this upwards closure will again be an ultrafilter. It's one of the things you have to prove. And yeah, this is fine, right? Because we don't, when 0 is in UV, we just say the product is not defined. It's a groupoid, so the product doesn't have to be defined everywhere. And then you'll notice that these basic open sets we had above are in fact compact open bisections with respect to this groupoid operation. And moreover, that these actually respect the inverse semigroup operations. So, I mean, they respect it, but in fact, the important thing, I guess, to note is that these basic open sets now are indeed closed under taking products and taking inverses, which remember was one of the ways of defining what an étale groupoid, or in this case an ample groupoid is, because these are all compact open bisections. Yep, question?
Quick question. Very top. U of S, maybe I'm missing something.
Yep.
You mean U containing the power set of S?
U containing the power
So
set?
the elements of, are you talking about an ultrafilter that's subsets or subsets of S?
I'm talking about an ultrafilter which is a subset of S, right, which is a maximal down-directed upset with respect to the canonical ordering in your inverse.
Well, I was saying is that the member of U is a subset of S, so U would be a subset of the power set of S, right? Because it's a collection of subsets.
It's not a collection of, it's a subset. Each ultrafilter is a subset of.
Okay.
I think.
Okay, I'll talk to you later about this.
Yeah. I mean, some people, when they're talking about ultrafilters, they only mean ultrafilters of subsets of some set.
Yeah.
But this is not what I'm talking about here. Yeah, I'm using this order relation you have in your inverse.
I got you.
Yeah. Okay, so yeah, upshot, this guy is a nice ample groupoid. Moreover, we can do the recovery thing we did before, pretty much in exactly the same way. So if you have one of these inverse semigroups now, which is already the compact open bisections of some groupoid, then each point determines one of these ultrafilters, just by looking at all those elements in your semigroup here, all those compact open bisections containing that element of your groupoid. Okay, and with respect to the topology you've defined, it's going to be, again, a homeomorphism, and moreover now it will also respect the groupoid string. So it will be a groupoid isomorphism as well. And again, this is basically the end of the story, right? You've shown that these two maps here, going from an inverse semigroup to ultrafilters, obviously going from such an ample groupoid to its compact open bisections, they really are inverse modulo natural isomorphisms. So this gives you the Lawson's non-commutative stone duality. Okay, and I have one more slide before we really get into the kind of new stuff. I just wanted to mention a couple of little facts about meets and expectations in inverse semigroups. So actually, first let's just consider a specific kind of inverse semigroup, one of these ones where it's formed from the compact open bisections of some groupoid. In this case, you'll notice that every such bisection, in fact, contains a largest idempotent. It's simply the idempotent you get by taking the intersection with the unit space. Because I'm assuming my groupoids are Hausdorff, so this unit space will be Kloefman, and so This will again get you another compact open bisection, the largest possible one, which is in the largest possible one just consisting of units. You can actually do something very similar even in an abstract inverse semigroup, as long as you have meets. If you have meets, then you can define this phi here just by taking meets like so. And this will again be the largest idempotent, which is below A in the inverse semigroup, the canonical ordering. Okay. The interesting thing is that there's actually a converse of this due to Lich. So if you do have this property, if you know that you can define this function phi, which is always the maximum idempotent below A, well then you know you have meets. You can define the meets explicitly using phi like so. So meets and these functions phi here are somehow equivalent, right? And these functions phi here have some nice little properties. They're properties you might be familiar with if you know about Cartan pairs of C-star algebras. So it's basically an expectation. So it preserves the product as long as at least one of those elements here is an idempotent, and itself it is also an idempotent map. And it has another couple of properties which perhaps Leach was not so concerned with, but also turn out to be quite important. So one is that it's shiftable in the sense that if I look at a product ABA, it doesn't matter whether I apply phi to the first guys or the last two guys. In fact, they'll end up being the same. It's sort of, maybe it's a kind of analog of a normality-like condition. And bistability is something similar. If you have a product and you already know it lies within the range of phi, in this case, if you already know it's an idempotent, then again you can apply phi to either one. You'll get exactly the same thing and it will again lie within the range of 1. So, and when you start moving into more general things, more general semigroups, more general rings, etc., it really turns out that it's more the expectations that are important rather than the meets, as we shall see. So just get a drink. So now let's dive into the good stuff, the new stuff. So remember I wanted to set up this kind of duality between ample category bundles and some nice class of semigroups. So first I have to tell you what the hell an ample category bundle is. So again, with categories I don't like objects, I'm just going to view these as groupoids without inverses. So we have a partial associative product, right? And we have the source and range map to units, right? And these determine when the product is actually defined. So that's a category. Topology on a category is again a tile if all the structure maps are continuous, open, and locally injective, and hence local homeomorphisms. It'll be important to define bundles that you know what an isocofibration is. So I didn't make up this word, don't blame me. This is some category theoretic terminology. And it's basically just a functor, right? In the sense that if AB is defined, then it preserves the products. But it's slightly stronger in the sense that if you know the product of row A and row B is defined, then in fact AB also has to be defined, and it has to be equal to that. Okay, so what is an Natal category bundle? Well, it's one of these isocofiberations. It's an open continuous isocofibration from a Natal category onto a Natal group. Okay. As usual, a right inverse, one of these guys, a continuous section, is simply something that satisfies this thing here. In particular, if you have a nice section and it basically absorbs everything wherever possible, then we'll call this a zero section. So the kind of bundles I'm going to be interested in satisfy these conditions. Maybe it's not immediately clear why I want all these conditions, but it will hopefully soon become clear why these are necessary. So an ample category bundle, in my terminology, is one of these Natal category bundles where, well, G has to be an ample groupoid, rho has to have a zero section, and moreover I want every fibre to contain at least one invertible element in here. So equivalently what I'm saying is that the map rho takes the core, the maximal subgroupoid of your category here onto G, still onto G. So that's ample category bundles. How do you produce a nice semigroup from this? again, you look at sections. So say we have...
Can you give an example so we have in mind something?
Give you an example of an ample category bundle. Well, I mean, basically, well, what's a good example? I mean, pretty much anything. If there's sort of trivial examples in the sense that you have a bundle of rings over a space. Any space can be viewed as a trivial groupoid. So, okay, forget about the additive structure of your ring. Then this will be a nice ample category bundle. What's a less trivial example? Well, what if you look at trivial bundles like over groupoids, let's say? So just look at I don't know, complex numbers, not tensor product, just Cartesian product with some groupoids, right? And then you can view sections of that as just complex value functions on your groupoid, right? And these will like, if you forget about the additive structure of C, then I guess this will again be an ample category bundle, right? Does that make sense? No? Yeah, I mean, maybe I should have thought of some better concrete examples to give you, but I mean, yeah. I mean, there's lots of trivial examples I could give you. I don't know, take an entire groupoid, just look at the identity map on that, things like this. But the point is it's meant to somehow generalize both categories and groupoids. Okay. So because we have a zero section, we can define the support of any one of these sections, right? All the points where it's not zero. And we can also define a product. So you might be used to defining the product when you're dealing with maybe ring value functions over a groupoid. But as long as you restrict to sections where at least one of those is a slice, then you don't need addition to define any kind of convolution product. You can define the product like this. Because for your G, as long as one of them is a slice, then there can be only at most one, H and I lying in these supports which satisfies this equation. So this will be well defined in that case. And you just set it to be zero everywhere else. Fun fact, that's the supremum of the product now with this definition will be compact as long as the supports, as long as the supports of A and B are compact. And so what this tells you is that if you look at these compact slice supported sections, then these form a semigroup under this product. Right. The next natural question you would ask would be, well, can you recover the bundle from the semigroup of compact slice supported sections? And here the answer is pretty simply no, right? That there's not enough structure in the semigroup alone to do this. And that probably isn't too surprising if you know about, Cartan pairs of C-stars, right? You know that different groupoids can produce the same C-star algebra, right? And this is why you need to look at pairs. You need to add this extra data coming from a certain sub-algebra. So maybe here we need to do something very similar. Maybe we need to look at some special sub-semigroup of this guy, maybe even some extra stuff, maybe an expectation, things like this. Maybe this will help us give us enough data to really be able to recover the groupoid and then build this up to a nice duality. Okay, so what extra structure does this have? Again, take some ample category bundle. Note that you get an expectation in the usual way just by restricting to the unit space. Right? I mean, I guess it's not exactly a restriction, but you're setting to zero outside all the unit space, right? You also have a special sub-semigroup, like I kind of hinted at before, where you look at sections supported on the unit space, but which moreover only take unit values on the support. These will all be idempotents, but they'll be very special kinds of idempotents. There may be others, so we'll single these special idempotents out and call them projections. Okay, you'll notice that if you have some other section which is supported on the unit space, right? So in other words, some other section which is in the range of your expectation, and you have one of these special projections, then it doesn't matter actually which way you take the product. So what this says is that these projections here lie in the center of the range of the expectation. Right? So I'm trying to give you these extra structures and show you a few simple properties that they satisfy in the hope that we'll eventually get a nice enough structure that really characterizes the kind of semigroups we're dealing with. This this stuff I mentioned before, bias stability, this also plays a role. So this turns out to be bias stable with respect to this expectation, and also normal in the usual, algebraic sense. Although maybe you're only used to doing it with groups, but it's a very natural semigroup generalization of what it means to be normal, just here. Okay, so this defines what I'll just call, for want of a better word, a well-structured semigroup. If you have a well-structured semigroup, this well-structured semigroup structure, this does in fact already give you enough structure to recover the groupoid. However, it doesn't quite give you enough structure to set up a real duality. To do this, we again need to look at a bit of order structure on our semigroups. So let's take some abstract well-structured semigroup. So semigroup S with a nice sub-semigroup projections, an expectation, satisfying a few simple algebraic properties. Then we can define some nice order relations. So we have the first one, which I'll call the restriction relation. This looks perhaps quite similar to what you're used to if you've seen the definition of the canonical order in an inverse semigroup. This other relation, domination here, maybe looks a little bit complicated, but instead of trying to explain sort of the motivation here, maybe it's better just to give you a couple of examples. So if you're looking at inverse semigroups, both of these just reduce to the canonical order. This domination thing here looks rather complicated, but in this case it reduces just to the usual ordering. The things that we're interested in, these ample category bundles, so you look at the structures you get there, where you look at sections, well then restriction does indeed look like restriction in the usual sense. It's simply saying that this section B here, when you restrict it to the support of A, is exactly the same as A. Domination, on the other hand, is more like saying that the support of A is contained in the support of B. But it's actually a little bit stronger than that. It's really saying the support of A is contained in, you might call it the invertible support, right? The elements on which this takes invertible values. So hopefully, you're basically defining domination like that so that this is true, right, in this setting. So let's look at a few more kinds of properties we can extract from these order structures here. So if we have A being a restriction of B in this sense, then in fact you can show that this means A and B have to agree on some Clopen set, right? And this allows you to define a kind of relative complement like so, right? So it's just B not A would be just B everywhere outside the support of A and just 0 everywhere else. So it's again a kind of relative complement in an order theoretic sense. Another little property to note is that you can always dominate sections by larger sections. The idea here is you have a slice supported section, and then one of these key properties, remember, of an ample category bundle is that every single fiber contains an invertible element. So then you can take some section which goes through that invertible element. You can actually do this with all of those points there, and then you can cover the support of A by finally many of these kinds of sections with compact support, taking invertible values, and then stick them together to get your larger section B. That's sort of the rough idea. We also, like before, we have suprema in this special situation where these two things are orthogonal, although in this case I have to define what orthogonal means, right? And it's sort of like before, it's essentially saying A and B are orthogonal if they have support projections on the left and right which are themselves orthogonal in the sense that their product is 0. That's essentially what this is saying. So with inverse semigroups, this is indeed the same as the orthogonality relation. When I say in inverse semigroups here, what I mean is if you take S to be an inverse semigroup, you take Z to be the projections, and you take phi to be the canonical expectation, as long as you have means. What about when you have an ample category bundle? Well then, again, you can characterize orthogonality in a very similar way to what we were looking at before, right? It actually just means that the supports are disjoint and the supports again form a bisection. Okay, and in that case, you define the supremum as you would expect, right? Then you would just say that this is equal to A on the support of A, it's equal to B on the support of B, and it's equal to 0 everywhere else. And these will indeed be suprema with respect to this restriction relation. And again, distributivity holds relative to the product, right? And well, I guess another thing to note is that suprema of these projections are again always going to be projections. So there's a lot of little properties here I'm mentioning, which I don't expect you to all remember, but just suffice it to say we're trying to isolate some very simple properties which will characterize these kinds of structures here. So let's just let's sort of put this in a nice, package this in sort of a nice definition. So remember, a well-structured semigroup was one of these triples where you have a semigroup, you have a shiftable expectation, and you have a nice sub-semigroup. So it's normal, bistable, and it lives inside the center of the range of the expectation. And the little extra conditions defining what I'll now call a Steinberg semigroup are as follows. So every element is dominated by some others, it has a zero, these are both distributive, they have all suprema, and complements. So the more sort of Boolean-like conditions. And so what we've basically shown is that whenever you have an ample category bundle, whenever you look at these sections here, that this gives you a Steinberg semigroup in this sense. So again, I know it's a lot of conditions to think of, but individually these are all pretty simple, they're nice, they're algebraic, so this gives you, I think, a nice algebraic characterization of these guys. So, and just a little point, I guess, I'm taking G to be Hausdorff, but I'm not taking C to be Hausdorff, right? And in fact, when C is Hausdorff, you get another simple algebraic condition, and that is that each element will then have a nice left and right support projection. And in that case, you have a restriction semigroup like I was telling you about at the beginning, right? These things looked at by Kudryavtseva and Lawson. So these Steinberg semigroups here generalize these Boolean restriction semigroups that they were looking at. Okay, so again, we want to be able to, we hope that we've isolated the right kind of structure to be able to recover our bundles. Right? So again, the way to do it, to recover the base space, you look at these sections here. So this time, given a point in your groupoid, you look at all the sections which take some invertible value. And these will indeed form an ultrafilter with respect to this domination relation. But you don't just want to recover the base groupoid, you also want to recover the fibers, right? And this you can also do in a kind of nice way. So whenever two sections are equal, they actually have to be equal on some clopin subset containing the point G. And that means essentially that you can find some other section in this ultrafilter satisfying this condition here. So once you know the ultrafilters, you have a nice kind of algebraic relation which tells you, which basically you look at the equivalence classes with respect to this relation, and that will recover the individual elements in each fiber. Okay. So fiber from G can be recovered from this equivalence relation, right? Okay, so that's the recovery part. So we're almost there. We're getting close, don't worry. The other thing, the next step is to take an abstract Steinberg semigroup and try and create one of these ample category bundles. And you do it like before. Look at ultrafilters. Products are defined the same way. You have to take up its closures just to ensure you get ultrafilters. I guess inverses are defined in a slightly different way because we're not dealing with inverse semigroups anymore. We can't just take all the inverses. So instead, we have to do something a little bit similar. We have to look at the elements which, these S's here, which witness the domination relation. Right? They turn out to give you precisely the right elements to give you inverse ultrafilters. Right? You can define an equivalence relation like we did on the previous slide, and then you look at pairs. These will give you the total space, and you can indeed define a product on them as you would expect. Right? I mean, you have to show this is well defined, right? You have to show that if I took different elements of my equivalence classes here, that again the product would be in the same equivalence class. But you can do this. So these form a category. The bundle or the map, right, that defines your bundle is very easy to find. It's just the projection onto the second coordinate. And you again want to give this a topology, and it's the topology you would expect. I mean, you're taking inverse images of the basic open sets here to ensure that this is continuous, and you're also looking at these kind of tubular neighborhoods coming from the elements in your semigroup. Okay, this is essentially to ensure that the sections I will define on the next slide are indeed going to be continuous. So yeah, we're getting very close, right? We've got these two maps. We can go from Steinberg semigroups to ample category bundles now. We saw before we can go from ample category bundles to Steinberg semigroups, but we haven't yet shown that we can represent the Steinberg semigroup here as sections on the ample category bundle. And that's what we need to do next. Okay, so take our Steinberg semigroup, look at this ample category bundle. It's very easy now actually to define how to represent it. Right? You just look at this function which maps any ultrafilter to the corresponding element of the total space where this first coordinate is the equivalence class defined by A. And what you can show is that this is indeed a semigroup isomorphism from the semigroup you started with onto all compact slice-supported sections of your ample category bundle. And it also turns the abstract expectation you started with into the actual canonical expectation you have relative to your ample category bundle. So it's preserving all the structure here. It also maps the projections onto the projections, the unit valued sections of your bundle. So it's all looking very nice. And this is basically it. So it took us a while to get here, but this is what we now have. So we really do have these two maps going from Steinberg semigroups to ample category bundles, going from ample category bundles to Steinberg semigroups, and they are indeed inverse to each other modulo natural isomorphisms. So this is the sort of one generalization of this Lawson's non-commutative stone duality. There are other generalizations, like with that have been worked out with Kudrat-Sever, etc. But this is the one that really turns out to be very simple to extend this to the rings that really motivated all this discussion in the first place. First, though, let me tell you quickly about the morphisms, because remember that was another one of our goals, right? We wanted to make these dualities truly functorial. So what should the morphisms be? Well, for Steinberg semigroups, it's natural that they should preserve all the relevant structure. So definitely they should be semigroup homomorphisms, but they should also preserve the projections here. They should also preserve the joins whenever they exist. And they should also respect the expectations. Whenever you have one of those, just like with the classic girlfriend duality or the stone duality, you then get a map in the reverse direction between the ultrafilter spaces. And it's very simple. You just use your Steinberg morphism pi here, get any ultrafilter, just take its inverse image. And again, just to make sure you have an ultrafilter, you have to take the upwards closure. But as long as this inverse is, as long as this is non-empty, this will again be an ultrafilter. So it's really a partial map, right? But it's a well-defined partial map between some open subset of the ultrafilter space to the other ultrafilter space. And moreover, it does indeed respect the groupoid structure, and then it allows you to look at a pullback of one of those bundles. And here things get, I guess, a little bit tricky, because then you can again use pi to get a map, not exactly from the fibers of this to the fibers of this, but the fibers of the pullback of this to the fibers of that, right? Which respects all the product structure. And they're a little bit complicated, I guess, but these were exactly the kinds of morphisms that Pierce and I guess later Dauns-Hofmann as well were considering when they were looking at their dualities for commutative biregular rings. Okay, so these extra things here actually allow you to turn this into a truly categorical duality. What about finally rings and ringoids? This was the whole reason we really wanted to do this. We didn't really just want to look at semigroups. So how do we define first what an ample ringoid bundle is? And it's basically like an ample category bundle with some extra additive structure. Right? Every fiber has to be an abelian group, and products distribute over sums whenever they are actually defined. Okay, and you also of course want the sum to be continuous wherever it's defined, right, relative to the topology, etc. Now you have sums. You can extend the product from slice-supported sections to arbitrary, compactly supported sections in the usual way via convolution. And you can extend the expectation. It's exactly the same. You just basically restrict to the unit space. Okay, and now we have not just a triple, but a sort of quadruple, right? We have this extra. We basically have a Steinberg semigroup sitting inside some larger ring. So it in fact generates the larger ring. So that we'll call, let's say, a Steinberg ring. How would you get from a Steinberg ring to an ample ringoid bundle? Well, again, with ultrafilters, again, define the equivalence relation, except now you can define the equivalence relation for elements even in this larger ring A. As the expectation is additive, so is the relation, and that means we can define an addition operation on our bundle, which turns it into an ample ringoid bundle. Again, we represent elements even of the larger ring now in exactly the same way. This will again give us a continuous section, and it will, again with a bit of work, you can show that it in fact maps A onto the entire collection of compactly supported sections of a row. Okay, and if you want to make it functorial, well then again you look at the same kinds of Steinberg morphisms and Pierce morphisms, with the extra restriction that they have to respect the additive structure. And then everything pretty much works out. All the hard work was really done already at the semigroup level. And you just check that the additive structure works, and then you have this nice final duality which encompasses this, this earlier work of Armstrong, as well as the more classical work of Pierce and Dauns-Hofmann. Right? So that's it.
Does anybody have any questions for Tristan?
These Steinberg semigroups, I presume that's after Ben Steinberg. Did he do anything with them? Or?
No, he didn't. Yeah, I wonder if I should really ask his permission to be able to use his name. But I mean, Steinberg algebras is what he looked at, right? So Steinberg algebras were originally defined as like locally constant functions defined over some ample groupoid. Steinberg rings, my invention, but they meant to sort of abstractly characterize algebraically some kind of generalization where you're looking at bundles instead of just a fixed scalar algebra with scalability of functions, I should say. And Steinberg semigroups are a further generalization, if you like, right? So the Steinberg ring, the Steinberg semigroup, he didn't exactly do anything with those, but I'm freely taking his name because they're kind of closely related.
So Ben Steinberg, because the semigroup theory now has two rings named after him.
Oh yeah? He has two rings named after him?
No, the algebra.
Is there another notion of a Steinberg ring or something?
Well, the Steinberg algebra.
Steinberg algebra, exactly. Yeah.
It's a ring.
Yeah. This is true. Yeah. But I mean, Steinberg algebras, they're not just algebras exactly, right? They don't have a nice algebraic characterization. I mean, I guess they do kind of now, thanks to this work of Armstrong and Steinberg, etc. Right? They at least found a nice algebraic characterization of the twisted Steinberg algebras. Right? But yeah, Steinberg rings are just meant to be a natural generalization of that.
Any other questions?
Yeah,
others?
So the relationship, say, between spaces and C0 of the spaces, like that duality, is really nice because it also has like K-theory, like K-theory on spaces and K-theory on C-star algebras are related. Are there like homology or cohomology theories? Maybe not for this one, but maybe for some of the other earlier dualities that pass.
Yeah, I mean that's a very good question. I haven't thought about that at all, but yeah, maybe maybe there is some more natural way of defining some kind of k-homology or whatever directly from the bundle, and then you would want to know whether it corresponds to the k-homology or whatever of the ring or the C-star algebra or whatever. Then yeah, I mean these are very good questions, but yeah, I don't know.
Thanks.
Any other questions?
Just a very quick, kind of vague question, but is there, much like with these letter path algebras, and I think even these Steinberg algebras, where you have these kind of dualities between graphs and algebras and such, I noticed that you've got some ultrafilters and Boolean algebras and various things sort of sitting side by side. Is there you know, are there studies where someone might say, hey, look, I'm going to look at a property of ultrafilters like being compact or uniform or something and translate that to something algebraic about the algebra?
Yeah, well, I mean, there is, and I guess maybe not exactly with ultrafilters, but there's this paper by Excel and Pardo where they're looking just at inverse semigroups, and they're looking at the type groupoid you get from that, which you can form from type filters, not exactly ultrafilters, but very, very close. And then they do look at certain properties of, like, you know, if the inverse semigroup has property blah, then the étale groupoid has property blah, right, like the type groupoid, right? And they have a few of these properties, and yeah, they look at the correspondences. And that's definitely something I would like to investigate further, is that, yeah, can you, now you have this nice duality, well, you know, what more can you say? If you place certain conditions on the bundle here, well, then this surely should have some translation to the semigroup or the ring, right? And yeah, this would be, I think, a very, very, that would be the next step. That would be the next thing to look at, I think.
Any other questions? Okay, let's thank the speaker again.